Hi once again. Let me explain where were we and what we will be doing. We are dealing with the second order circuits, and we have found a mathematical model of these second order circuits on an example. That was our example circuit, that is parallel RLC circuit. The corresponding mathematical model is this differential equation. This is ordinary differential equation. So the next step is how to calculate that. So we said we could use the methods that we learned in the differential equation course. We call it mathematical solution. How you can find the solution? You're going to find the homogeneous solution first and the particular solution. The second step, add them up, you get the general solution. The difference between the first order and second order, in this one, in the homogeneous solution, we have 4 parameters needs to be calculated by using the initial conditions. But initial conditions, since it is the second order, it is just 2. So 4 unknowns, we've got these k unknowns here, and we've got 2 knowns related to initial condition. So we said we could do something different from the mathematics that you already done. We can calculate a new initial conditions for the derivatives. How we could do it, that's easy. That is the differential equation. So if we replace t with 0, right hand side becomes this. These are the initial conditions. This is A matrix, this is B matrix. When t equal to 0, this is also known. So the right hand side is known, left hand side is the derivative function's initial conditions, isn't it? So I found you another 2 initial conditions. So altogether we have 4 initial conditions, 4 unknowns. We can find out all these k values. This is what we said already. Now we are saying, up to now we examined all these example circuit by parametric analysis, isn't it? These are element values is not included here. Why we have done it here like that and then we left the numerical solutions later on? Because we said this homogeneous solution includes the characteristic roots. Depending of the characteristic roots type, what does this mean? Real, complex, or the multiple roots. Our solution functions format is changing. Therefore, we would like to give you those 3 different type characteristic root case solutions. So that we call this solution is as the second step. In the second step, we already examined these real roots case. We also examined the complex root case, and now we came to multiple root case. This is that case. So, conclusion now. We will be examining, solving a second order circuit when the characteristic roots are multiple roots. So let's see it now in the open board. That's the case. This is the circuit given to us. That's the second order. There's 1 inductor and 1 capacitor in it. And this is the mathematical model, which is the state equations related to that circuit. So if we choose the element values like that, then these characteristic roots are going to be multiple. So I can show you the calculation. So this here, that state equation is the numerical state equation. That means element values have been replaced here. So this is the numerical state equation. So how we are going to find solution? Of course, we are going to get the homogeneous solution first, homogeneous, and then particular solution. Add them up, we are going to end up with general solution. So let's do the homogeneous solution first. Then we are going to find the characteristic equation. That is the characteristic equation equal to 0. That I is the unit matrix. So S time I is this S 0 0 S minus A matrix is this matrix. That is A matrix. For numerical one, that's the parametric one. So minus 2 10 to the power 3 minus 8 10 to the power 6 125 10 to the power minus 3 0 equal to 0. So that's going to be S plus 2 10 to the power 3. That minus is going to be plus 10 to 8 power to the 10 to the power 6. And this is minus 125 10 to the power minus 3. And that is S. Determinant of it is equal to 0. Then S square plus 2 10 to the power 3S. Now it's going to be plus, because multiplication has got a minus in front of it, so it's plus. That's 1000, that's 1000 disappears, 10 to the power 6 equal to 0. From that, if you calculate the characteristic roots, you're going to get minus 1000. The other one is minus 1000. So it is multiple roots. So in this case, our homogeneous solution is going to be VCIL. Let me write the homogeneous at A. Let's represent homogeneous solution. So K1 1, K1 2 1, sorry, e to the power minus 1000t. When it is multiple, K11, if you remember it from the K12, K22, from the differential equation course, it's going to be t times e to the power minus 1000t. So for this root, and for the same root, but there's going to be a t in front of it. So that's the homogeneous solution. Then we've got to calculate the particular solution. If you remember, source is DC. Here you are, source is DC. If the source is DC, our particular solutions are going to be DC. That means all the elements, current and voltages, are going to be constant. Then if you consider the definition relation for inductor, it's going to be this. So since I is a constant, derivative of it is 0, so VL is 0. VL is 0 means short circuit. So capacitor definition relation is this. In this case, if the VC is a constant, derivative is 0, then IC is equal to 0. So that is open circuit. So if you apply this, this is going to be open circuit, that means removed, and this is going to be short circuit, goes like that. And since the inductor is connected to the resistor in parallel, so resistor voltage is equal to inductor voltage, which is 0. So definition, voltage of the resistor is 0, then current of the resistor is 0. When both of them 0, this is going to be open circuit as well. We already explained all that. So this open circuit, so that current passed through the inductor. So inductor current is equal to this current. So that means to this current, isn't it? So particular solution for the inductor IL particular is 1 amp. What about VC particular? So this voltage, inductor voltage is 0. The capacitor is connected in parallel to the inductor, so its capacitor voltage is 0. So that's the particular solution. So that's going to be 0. So if you add, this is the homogeneous solution. If I add particular solution to this, capacitor is 0, particular solution. Inductor is 1. The underneath is the inductor, so I put the 1 here. So this became now, I'm going to cross this and make it now general solution is equal this part a homogeneous solution, that is. And that is a particular. So this is our solution now. From now on, what we are going to do is just to calculate these k values. So how we are going to calculate the k values? We said we need to calculate the derivatives initial conditions. We've got two initial conditions here. Capacitor voltage, one of the initial condition. The other one is the inductor current. So I need to calculate the derivatives initial conditions. How I am going to calculate it is easy. So in here, this is the numerical state equations. So you're going to replace this t equal to 0. So when t equal to 0, that Vc is going to be the same as this. So that is 0. And that one is going to be this. That means 0.5 amp. So right hand side is a numerical value. If you do the calculation, you're going to end up with that capacitor voltage derivative initial condition is equal to 12 10 to the power 6. And this underneath one is going to be equal to 0. So right hand side is 0, that's why it is 0. So I have calculated this capacitor voltage derivative initial condition 12 times 10 to the power 6. Inductor currents derivatives initial condition is equal to 0. So how I am going to do the calculation is not so difficult. Why is that? I am not going to write 4 equations and find the 4 unknowns. I am going to divide it in 2 groups. First one is writing this voltage, capacitor voltage function, VCT is equal K11 e to the power minus 100t. That is 1, 1. That's this one. And K12 t times e to the power minus 1000t, the second one, plus 0, I don't write that 0. So in here, if you replace t with 0, it's going to be initial condition. Initial condition is 0, isn't it? So you could move the initial condition here, 0, for this, equal t equals 0 to t e to the power 0 is 1, so k11 plus 0, isn't it? Because that t, when you multiply it with 0, so this comes 0. So conclusion is k11 is equal to 0. So this is the first equation. How I'm going to get the second equation? Get the derivative of this. It's going to be dvc over dt is equal. Derivative is k11 minus 1000 e to the power minus 1000t. And the second one, multiplication of 2 functions. So derivative of this function is 1 multiplied with the others. 1 2, that is, make it e to the power minus 1000 t, and the derivative of this function multiplied with the other function, so k12 t minus 1000 e to the power minus 1000 t. Nothing else. Now what I am going to do, replace t with 0, t equal to 0, right hand side t equals 0. So that is capacitor voltage derivatives initial condition. We already calculate this. Here you are. And this one here is going to come here. 12 10 to the power 6 is equal, t equals 0, that means that is 1, so minus 1000 k11. So this one, t equals 0 plus k12. And this, when you replace it with t, this term becomes 0. So that's the second equation. So two unknowns, two equations. You can find the k11 and k12. So what we have done, we considered only one variable and then get this variable derivative. Two unknowns, two equations. Find out the parameters related with this variable. So that means k11 and k12 parameters have been calculated by using two unknowns, two equations. Okay. So I left to you to do the same thing for the second state variable, IL. You're going to repeat it for IL. You're going to write IL as a function, and then you're going to get the derivative of it, and then replace with t equal to 0. For this one, derivative's initial condition is 0. You're going to find out two unknowns, two equations, calculate k21 and k22. At the end, what you get is, that graphic. So here you are, capacitor, we already done it. So if you draw this this graph now related to that function, so you end up with a function like that. Since the particular solution is 0, there's no particular solution. That is the homogeneous part of our solution. Homogeneous part is the transient solution, and it disappears after a while. So after a while means after 8 milliseconds it disappears. So we cannot observe any value at all because the particle solution is equal to 0. But critical thing that you've got to pay attention is this. In the range of 1 millisecond here, we are going to observe a very high voltage that is in the range of 4200. There is no that much voltage within the circuit, but this is observed here. On the other hand, I know that this voltage will be observed for a very short time. You see that here, maybe in the range of microseconds, you're going to observe that voltage, and then it immediately goes down. So that could be critical for your circuit if the limits of your capacitor voltage is less than this. Let's say your capacitor voltage range is in the range of 1000, so that means you're going to see 4200 volts on that capacitor. Maybe it will burn. We don't know because we need some more information. Why I said we don't know? Because you're going to observe this very short time. Maybe it's not going to burn, I don't know. You've got to examine the manufacturer's specification in order to make a decision like that. So this analysis tells us that don't consider that transient solution is not important. So it could be important. It is an example for you. But in general, I could say that in electrical circuits, that means high power related electrical circuits, you might face, you need this transient solution examination in detail. But electronic circuits, we don't have that big powers, maybe you don't need that. In general, we don't need the transient solution or homogeneous solution, we might say. So, as I advise you to do the inductor currents calculation your own, if you do it, you end up with a function like that. If you look at that function now, you can observe particular solution, because particular solution is 1. That is the homogeneous solution. After 10 milliseconds, you don't observe any transient solution at all. This solution not observed after that time. So what you're going to observe is that constant value, that particular solution after 10 milliseconds. Before 10 milliseconds, so there is a change here, that is a transient change. So if you look at the beginning of this curve, start from the initial condition. If you remember, the initial condition for the inductor was minus 500 milliamp, so that is where it is. So it starts from that and goes to that particular value, and you must remember that inductors currents cannot change instantaneously. It doesn't change instantaneously because this starts from here. Just before that, your initial condition is there. There is no instantaneous change, means there's no jump. So that is the end of this video then, and escape from here.